Hi class, this video is going to talk about fluvial erosion. Fluvial processes are the first type of erosion we're going to talk about. And remember, erosion in itself is a three-part process, right? So some agent of erosion, in this case running water, is going to remove sediment. It's going to remove rocks, and it's going to then transport that sediment someplace else where it will deposit it. So you can think of erosion as the removal of sediment, the transportation of sediment, and then the deposition of sediment. So our goal is to figure out, well, how does it work? How does it remove it or transport it or deposit it? We also want to look at the landforms that are created as a result of this process. So some landforms are going to be created because running water has removed everything around this landform, and that would be an example of an erosional landform. Another example would be landforms that are created by this running water depositing sediment, building up a landform. And so we're going to look at fluvial erosional landforms and fluvial depositional landforms as well. Not during this video. This video is just going to kind of introduce you to the concept of fluvial erosion. There'll be another one that talks about the work of water. There'll be another one that talks about how water, that is, manipulates and modifies its valley. And then finally one about floodplains. So this one is just going to be like the introduction to fluvial erosion. So water is one of the most effective shapers of the land, in part because a lot of land is water soluble, so water can dissolve a lot, and water is ubiquitous, is found in many locations. And so with the help of gravity, pulling water down a slope is pretty effective in shaping our land. So when we talk about fluvial erosion, you can look at the screen in front of you, and this is an overhead shot of an area. So here is a stream, and what we can see in this image is that the stream isn't always in this particular location. What do you see on the screen that tells you that maybe this water that's been running in a defined channel was someplace else? Maybe you notice, let me get my pen, this feature over here. This is an oxbow lake. Here's another one. What do they look like, these kind of crescent moon shaped features? There's one over here as well. Over here. How did they get there? Well, this river, as it meanders back and forth, has been eroding the landscape. These kind of crescent moon shaped objects used to be river meanders, and the river has changed course, it's moved, it's eroded more, and so they are what remains. So we're going to look at how that works. Let's look at another image. So here's another image of a stream, and I did post a video again from Yosemite Nature Notes about the Tuolumne River, and I think it's a great introduction. You don't have to watch the whole thing, but maybe the first 7 to 8 minutes where you can actually see running water. And when you watch that video, I would encourage you to look at how the water is different when it's coming down a steep slope or when it is moving in a flatter surface. So if we look at this particular river, again, it's meandering. See how it swings back and forth? This is a meandering river. We can see areas where deposition, I'll just put a D here for deposition occur, and over here we don't see that because this is where erosion occurs. Here's one of those oxbow lakes, so you can kind of see in this image that the river used to go around here and then it's been cut off. Now this is very different than this image. What do you notice about the image on the right? Maybe you said, well, it looks like it's a steeper slope because I see in the background here like a waterfall, when I don't see anything like that in this picture. Maybe you notice that the actual river is it's not completely straight, but it doesn't wind and meander as much as in this image. And that's because when we look at the work of water, and how it modifies the valley and the land that it's flowing over. When we have a steeper slope like this, we get this kind of V shape here, a V-shaped valley. It's going to downcut to make this V even deeper. But when the gradient is not so steep, it goes to lateral erosion, meaning side to side, so it meanders, eroding the land back and forth as it meanders across the landscape. So when we talk about fluvial processes, we're basically talking about water that is flowing in a defined channel. In other words, a stream. For the purposes of this class, we're not going to get into what's the difference between like a brook and a creek and a stream. Or a river. We're just going to call it a stream, okay? There is a process by which water running over land also erodes the land, but that's called overland flow, and in a couple of slides I'll show you an image of that. We're not going to concern ourselves too much with that either. So I want you to really, when you focus your reading this time around, look at the study guide that I've posted, because it will tell you specifically the pages I want you to focus on in chapter 16. Okay. So let's start by just talking about stream systems. So what we want to understand is how streams are organized. What do we call the geographic area where they drain? What do we look at in terms of how they are organized? Are they nested? Are they singular? All of that, the hierarchy, if you will. We also want to understand how we measure stream flow. So all of these kind of basic understanding of how streams work is what we're going to cover in this video. And you're like, well, I'm already 7 minutes in. I thought you were going to cover it already. We're getting there. All right, so here's a picture of the Grand Canyon. I already showed you some of my pictures of the Grand Canyon. And so the Colorado River, has carved this landscape. So we're going to try to figure out, well, how does that work? So first, the organization. When we look at streams, we talk about the geographic area as the drainage basin. So the drainage basin, here in my example, there are two. This entire area over here is drainage basin A, and this entire area over here is drainage basin B. The definition of a drainage basin is the geographic area that's drained by a river. If you watch that Yosemite Nature Notes video, instead of using the word drainage basin, they use the word watershed. So that's another word for drainage basin. So we can see a couple of things here. This is the valley where the stream is actually running. The elevated area on either side of the valley, that's called the inner fluve. When we have rain, let's say that falls right here, it's going to flow over the inner fluve and into the valley. So that overland flow I was talking about happens here on the inner fluves on both sides. But as I mentioned, we're going to focus on the work of the stream in the valley itself. The headwaters, that's the beginning of a stream. You can see that this drainage basin is separated from this drainage basin by this elevated area, this dashed line. This dashed line is called the drainage divide. The drainage divide is the elevated area that separates two drainage basins. So, for example, let's say we had rain that falls right here at this star. Which drainage basin will that water ultimately flow into? Not drainage basin, but which stream? X, or this one over here we'll call Y? Hopefully you said X. Now, why did you say X? Maybe you said, well, water flows down slope. You would be right? Water can't go up and over the drainage divide. So it has to flow down into the actual river that occupies this valley. Why do you think it's important for people to understand how river valleys are organized? Well, let's say that you happen to live over here and you have a polluted water source. So you go to your city council and you say, well, we have a polluted water source. We need you to investigate. So they said, sure, no problem. And next thing you know, they're over here investigating everything that's going on in this drainage basin. Are they most likely going to find the source of your pollution over here? No, because your water is polluted by something that's probably occurring over on this side. So it's important to understand the drainage basin. Now, close to the college, close to the Santa Ana, Santiago Canyon College is the Santa Ana River. So the Santa Ana River starts at like Dollar Lake up in the San Bernardino Mountains, and it flows past these cities like San Bernardino, Riverside, Anaheim, Santa Ana, where it enters the Pacific Ocean here at Huntington Beach. The headwaters are up in the San Bernardino Mountains, and the mouth of the Santa Ana is over here at Huntington Beach. So it flows about 100 miles, and it goes through an area that's shown here in this light yellow, that's home to like 4.8 million people. All right, so it's not a very large drainage basin. It only drains about 2,650 square miles, but there are a lot of people who live in this area. So maybe you have gone hiking in the local mountains and you've seen the Santa Ana River there. It probably will look very different to you than if you've ever ridden the Santa Ana River Trail by like Yorba Linda, Anaheim, Santa Ana, all the way to Huntington Beach. You might also notice if you've ever driven on the 91 freeway between Yorba Linda and Corona, like the big dam out there in Corona. So there are actually two dams on the Santa Ana. One is up here in Yucaipa and one is in Corona. The San Jacinto is one of the tributaries. The definition of a tributary is a stream that contributes water to a river. And the Santa Ana has like 50 tributaries. The largest one could be the San Jacinto if it flowed all the way to the Santa Ana. Under normal conditions, it actually terminates here in Lake Elsinore, but if it's a year with a lot of precipitation, it'll continue to flow on to the Santa Ana. Now let's think about the Santa Ana River compared to the Mississippi. The Santa Ana River is the largest river system in Southern California, but let's compare it to the largest in our country. So the Mississippi River. So this diagram's from your textbook, and it is the second longest river in the U.S. It has a length of just about 2,300 miles from its source, which is, if we can follow up here in Minnesota, and it goes all the way to its mouth at the Gulf of Mexico. We say that it's part of the Missouri-Mississippi River system. So you can see up here in this first map, this is the entire area that's part of the Mississippi River drainage basin. And its size is 1.15 million square miles compared to the 2,600 square miles of the Santa Ana, so considerably larger. We can look at all of these tributaries to the Mississippi, like the Missouri River is a tributary, and the Missouri River's drainage basin, right here in light green, is nestled or nested inside of the Mississippi River drainage basin, so it's hierarchical. We could talk about the Arkansas red-white river basin or the Ohio River basin, etc. If we look at the Missouri River, it too has tributaries, and one of them is the Yellowstone River. So this is the Yellowstone River drainage basin, which is nested inside of the Missouri River. The bottom line is water that's going to flow into the Yellowstone River is going to be funneled to the Missouri River and ultimately to the Mississippi River and then on to the Gulf of Mexico. Okay. When I was in New Orleans, I like to go to museums, and so I went to one about the Mississippi River. I know, very exciting. And I like to take a picture of signs when I'm out at museums. Hold on, my husband just came home and the dogs are greeting him. So sorry if it's a little noisy here. So you can clearly read this, but I think that I'll just read some of it for you because I want you to think about the fact that a drop of water falling in the Rockies of Montana will travel about 3,700 miles en route to the Gulf. The total volume of water discharging into the Gulf of Mexico is 450,000 cubic feet per second. And it brings a lot of sediment, 406 million tons of mud. And if you think about it, where does that mud go? It goes to the mouth of the river where it builds up land. So all this part of South Louisiana has been filled in by sediment carried by the Mississippi River. Another thing I want you to think about is the term continental divide. So what do you think the continental divide is? Here are some pictures, so maybe you can look at the picture and think about what it might be. The continental divide is basically a drainage divide for a continent. It is what separates water flowing from one ocean to the other. So here I am in the Rockies, which are the North American continental divide. And basically, I'm looking to the south, and my son was a good sport and sat here. And so it says, water that falls on this side will flow to the Pacific Ocean, and on this side to the Atlantic Ocean. Close to this area, a little bit farther up in Canada, is a triple continental divide. What do you think the third ocean is? Yeah, the Arctic Ocean. One day I was driving through Yellowstone, I saw this, so here's another example of the continental divide. If you happen to have signs like this, if you've been out and about and you've seen them, send them to me. Another term that I want you to understand is perennial and intermittent streams. So a perennial stream is one that always flows. An intermittent stream is one that does not flow all the time. It usually flows part of the year or after a storm. In this these pictures, which one do you think is the perennial stream? Yeah, the one on the left. Now you might look at this image and say, well, I don't see how water can do work in this area because it's not flowing. But when it does flow, it has the ability to move a lot of this loose sediment. So in this class, we're going to use intermittent and ephemeral interchangeably. Basically, an ephemeral stream runs after like a storm. Intermittent just runs part of the year. And so we're just going to use those to mean a river system that's not running all the time. Now with regards to stream flow, when we talk about the amount of water flowing in a stream, we use the term stream flow discharge, and we use a capital Q to denote discharge. So here is a picture of like a river gauge, and you can see that it's recording all this information. This is how hydrologists understand water systems, and they record a lot of data such as discharge. Here's a cross section, so you can see that a river has a width, it has a depth, and then it also has a length. But for the term discharge, what we're interested in is this cross section here. So this area in blue has a width and it has a depth. And then when we measure the amount of water flowing past that, the velocity of that, when we multiply them all together, we get discharge. So basically, it is depth times width, that's the area, and then area times velocity. So let's look at this. So stream flow discharge. Q for discharge is the width times the depth times the velocity. And we can use the word area here. So the stream's ability to do work has a lot to do with its velocity. Where we have water that's moving faster, we're going to have more erosion. So if we say if it's moving faster, high velocity, we're going to have more erosion. I'll just say E for erosion. If the velocity is slower, so less velocity, what we're going to have is more deposition. And this is going to be key when we talk about landforms. So if we look at just some numbers, this is a very small stream. So we just say it's 20 cubic feet per second. where do we get these units of measurement? Think about width is measured in feet. Depth is also in feet. So when you multiply those together, you get feet squared. And then velocity is measured by the amount of water flowing at a rate of feet per second. So when you multiply feet times feet times feet, you get cubic feet per second. So that's how it's calculated. So my hypothetical very, very small stream is 2 feet squared. That's the area. And the velocity is 10 feet per second. So I want you to think about what would happen if we kept this number the same, but we changed one of these numbers. So let's just say Q remains the same, 20 cubic feet per second. But instead of having an area 2, the area goes up. So the area gets larger. What's going to happen to the velocity? It has to go down. So if we keep this the same and the area goes up, velocity is going to go down. And that is important because when water flows into a large body of water, what happens to the area? So if we think about it like this, we have a stream flowing into a lake. What happens to the area here? The area goes up. So if area goes up, but Q remains the same, what has to happen to the velocity? Right here. It has to go down, and that's what these numbers are telling you. And if velocity goes down, right here, what do you think is happening? Erosion or deposition? Well, if velocity goes down, deposition goes up, so we're going to see deposition happening there. What about on the other side of the lake? The area was large, now it's been funneled to a smaller area, so area goes down. And again, if the amount of water flowing remains the same, what happens to the velocity? The velocity has to speed up. And if velocity speeds up, what are we going to see? More erosion or deposition? More erosion. So that's why it's important for us to think about this going forward. Where is the water running the fastest? That's where we're going to find the erosion. Okay, so in this picture, Q has gone up, and what do we get? A flood. A flood is when the water overflows the stream channels, okay? And you can see this is the Missouri River, a tributary of the Mississippi River. This is one of those cloverleaf highways, so it's been flooded. Now, when we talk about flooding, think about it. The area goes up and the velocity goes up, and so it's able to carry a lot more sediment, right? And it's able to do a lot more damage, truthfully, when we have a flood. So let's talk about a flood recurrence interval. If you live in a 5-year floodplain, you're saying that it's most likely that you're going to get a lot of flooding, every 5 years or so. If you live in a 100-year floodplain, you're less likely to get a flood because it's going to have less frequent type of event. Which one do you think, though, is a larger flood event? The 5-year flood or the 100-year flood? Yeah, the 100-year flood. So basically, the flood recurrence interval, the more infrequent it occurs, like 100 years or 500 years, the greater the flood that happens. Now, in Southern California, flooding isn't good for cities, right? It's probably not good even in a less populated area, but basically we have these channelized streams. So if you look at this image here, this is the LA River. Isn't it lovely? Maybe we have a picnic down there. Why do you think that the LA River has been channelized. And we call channelization when they put concrete on the sides. Sometimes they put it on the bottom just like this. Well, maybe you're like, well, Miss Engstrom, I see right here for maximum velocity. Yeah, it's a flood control. When water runs in the city, there are a lot of impervious surfaces, so we have a lot of runoff. They want to get that water out of the city as quickly as possible, so they create these channelized rivers. They are designed for maximum velocity, and they're pretty good. Um, but unfortunately, what happens is if all that water is moved out of the city, out to the ocean, then we can't recapture a lot of that water, right? There's nothing to let it sink into the ground and recharge underground aquifers like in North Orange County. That's why water districts actually have a plan for inserting water back into that underground aquifer. So basically, if we look at channelized streams, they're there for flood control. What would the LA River, though, look like without this lovely um, channelized area? Well, we have some LA River before channelization diagrams, and you can see that it's a dry river. It didn't always run. And when it did run, though, it would sink in. It could go to the underground water. They took some of the water over here for farming. Here's a picture of what it looked like. Wasn't it lovely then? I mean, this is what the LA River used to look like. You can see the natural vegetation, the natural bottom. So a little different than the channelized version I showed you. But don't despair, they're actually restoring the LA River, starting up by the Arroyo Seco, up by like Pasadena. And this is what it looks like now. People can kayak there, birds are coming back. Because what water managers are finding is that flood control practices aren't necessarily great for the environment. They're good for the built environment sometimes, but not necessarily for the natural environment. Okay, well, take care.